So,
All right.
welcome everybody to the second half of this day. So, we'll start with our hands on session, and Deepesh is here. He will take it forward. So, Deepesh, on to you. Thank you.
All right. So, hello. Last time we could not start the event. So, yeah, what I've done for this particular session is I have taken the meteorological data and we'll try to build a model from it. So, let's see. So, what we are going to do is, everyone can hear me? Can everyone hear me?
Yes,
Can
sir.
someone confirm? Okay, fine. So the problem I have taken is we all know that the precipitation is a function of many variables, and we can just let's just take few of the variables such as SST, precipitable water, OLR, and heat fluxes, and see if we can build a model to predict precipitation based on these variables. So uh, I hope you people have installed the libraries like scikit-learn, Keras, or TensorFlow. If not, I'll show you how to do it this time. Uh, you must have also got the data from the link I shared. One second, I'll have to. So I have not put the link here, but I hope because last time I shared it with you, people have must have downloaded the data, all the NetSedia files, and how we are going to go about it is basically first we'll just plot the data, see how it looks, what is the kind of relationship that we are expecting, and then we'll try to build a model out of it. And yeah, so the last time, I mean, from yesterday, I have been getting some queries regarding uh, people have been trying to basically install the libraries and they were facing some problems. So what I'll suggest is when you basically use a machine, even in Pratyush or your own machine, you set up your own workspace so that when you install a particular version of library, you don't face mismatch errors from other versions. So for that, what you'll do is you'll make a directory called at your home directory called ml, and you can just export it as like this. Then yeah, so these are the requirements for today's one. Jupyter, NumPy, Pandas, Matplotlib, scikit-learn, and so once again. All right. So once you have done that, you have made the library. You go ahead and install this virtual env, virtual environment, using this command Python 3 minus m pip install minus minus user minus to virtual environment. Then you basically go to the directory that home ml and you create your own virtual environment called my env, my underscore env, using Python 3 minus m virtual environment space my environment dot env. Now once you have done that, you have to go to the directory dot ml and you have to source the activate command. So basically just say source my underscore env bin activate. And I mean, after the entire session, when you are done with it, you can just log out from your Jupyter notebook and say deactivate. So that should basically stop everything. And now once you are inside, once you have activated the environment, then you can basically say uh, install these libraries on my local environment. So Python 3 minus m pip install all these libraries. The one error that I faced, and I think the other users also are facing, is related to GEOS package and PROJ project. So in my system, in my case, at least in Ubuntu, when I was working on my local PC, I could just install this libproj dash dev package, and libgeos ++ dev package. Depending on your operating system or on the machine that you are working on, it might change. In case of if you are working in Pratyush, I don't think you face this error at all. So once you are done with this, you have activated this one and installed the libraries, you are good to go. One thing that you have to do is you have to register your virtual environment with the machine. So you just type this python key -m ikernel install user name python key, and after that you can just start the Jupyter notebook. So you all know how that looks. Basically, this is how your Jupyter notebook looks. So I have in the link I have already provided one of the notebooks. So you have to go ahead and you can open it in Jupyter notebook. Okay. Why is it showing into your information? Okay. So once you have opened this, this is the complete uh, notebook. The one I have shared with the users is not complete. It has fill in the blanks for the users to fill in. So suppose that the data that you have downloaded, you have put it in your own path. So you are basically supposed to change that path to your path and run these commands again. So you import so to start with, you import NumPy, and I imported NAN from NumPy because I was dealing with SSTs, and SSTs don't exist over LAN. But that created a lot of problem for me. So ultimately, what I've done is for the data, for SST data, I have taken skin temperature, which from NCEP, which basically is SST over the ocean and the land surface temperature over the land. For plotting, we'll be using matplotlib. So import matplotlib.pyplot as PLT. Also import pandas because we'll be needing data frames in between. We will be using Xarray to open and read the netcdf files. You can also import warnings. It will show you more information when you are doing something wrong or you are getting an error. And for the map beneath the data, we are using cartopy. So yes, so import cartopy.crs as ccrs. Now here we have 5 variables. One is precipitation, SST, precipitable water, that is the integrated water over the column, outgoing long wave radiation, and latent heat flux. So what is observed is when you have higher SST, you have higher probability of precipitation. Uh, total Having total integrated water vapor higher is also increases the precipitation. OLR is basically when there is a low OLR, it refers to deeper clouds, and latent heat flux refers to the moisture flux at the surface. So what we have done is we have divided the data into two. From 2010 to 2009, actually, it is not 10, 2009 December, we are taking the climatology. So, this is our training data set. And for testing the model, we are using the data from 2012. Now, the precipitation variable itself is in kg per meter square per second. So you convert into millimeters per day by multiplying it with 86400. You can open all of these variables. So when you open it as xr.open underscore dataset, it opens it as a dataset and not a variable. So dataset you can assume as an entire file. Zoom in. Okay. So is it visible now? I have zoomed in. Is it better?
Yes, sir, it is fine.
All right. So yeah. So I was saying the precipitation is basically kg per meter square. So you convert it into millimeters per day. And you can look at all these variables. So when you open it, it is opening as a data set. So data set is basically the entire set, and it contains within it the details of latitude, longitude, and time. So since this is a climatology, we have 366 time steps. We are looking at the entire topics, but from minus 39.5 to 39.5, basically minus 40 to 40. But so this is 80. We have 1 degree data, and if you look at PREC underscore train, you have a variable named P rate. So this is the precipitation, and its dimension is time, latitude, and longitude. Now you to plot to basically initially get the feel of the data, we'll just take the mean of. So this is daily climatology data. So we will just take the mean of it entirely, and the way you can do it is say the data set dot the data array, that is the variable name, so p8 dot mean, and you are averaging it over the dimension time. So you can do the same thing for precipitation, SST, OLR, precipitable water, and LHF. And we'll do the same thing for test data also. The the thing is, the test data is for 2012 daily data. It's not the climatology. For plotting, many users will notice that this particular part of code is a little bit different from what I've shared in the notebook. Basically, what I did was I increased the size of the plot and change few things here and there. So this might be different. You can change your code accordingly, and that should be fine. So for Cartopy, you need latitude and longitude arrays, and basically you can just say PLT underscore PLT dot figure and change the size of the figure. So in the notebook I have shared with the users, the figure size is very small, so I've increased the size. Now, basically, you can just define a plot like this using projection from Cartopy SACRS, and you are going to define the coastline. So we'll see the coastlines here, and this is how you plot the variable. So PLT dot. So we are using color mesh. So X dimension, Y dimension, the variable itself, and the color bar that you want. So color bar is rainbow. You can set the title as training surface. So we have this because we have this one. We are plotting the precipitation, training surface precipitation. And to set the color bar at the right, you can just say, so you are defining the entire plot like this. You just ELT dot color bar, and depending on the size of the color bar that you want, you can shrink it or change it. And you are basically defining this unit also. So looking at the figure, what you find is you have a lot of precipitation near the tropics, I mean over the tropics obviously, and then you have very low precipitation over the Saharan region and our own Rajasthan region and all. So you have a lot of convergence here and basically subsidence on over these regions. Correspondingly, when you we similarly plot the other variables. So let's start with the OLR. So when we plot the OLR, what you'll see is corresponding to the regions where you have high precipitation here like this, you have very low OLR, and wherever you have very less precipitation, we have very high OLR. Similarly, looking at the SSTs, so SSTs are higher over the regions where you have high precipitation, but then the SSTs don't show very sharp characteristics similar to the precipitation. So you don't have very sharp gradients here. You will always have weak gradients here. Similarly, looking at the precipitable water. So the entire column, if you integrate, you have precipitable water. So wherever you have more precipitable water, you'll have chances of getting higher precipitation. And looking at the latent heat flux. So one of the studies that we were doing recently showed that latent heat flux is very important for getting at least the shallower clouds. And if they those shallower clouds can convert to deep clouds, and we should have higher precipitation. So if you look at this latent heat flux, it is higher near the tropics, but it's not really coinciding with the region of higher precipitation. You see like this region and this region, but it is somehow correlated to it. So what we'll do is from the data array, we'll just extract the values of these variables, precipitation, PVAT, OLR, and all, and we'll do simple scatter plots to see what is the kind of relationship that we get from precipitation and other variables. So if you look at uh, keep in mind that this is reanalysis data and not observations. Observations were really high resolution, and to basically train the models for it was going to take a long time. So just I'm just using the reanalysis data here. So if you look at the SSTs and precipitation, what you'll see is so here you also have the skin temperature. So when you say how are we getting very less the temperatures, this is basically because of the land surfaces getting very cold. But if you look at the SSTs, you have higher precipitation events uh, constrained to very specific SST region. Similarly, if you look at the precipitable water, that entire column, you have to have a very specific value of precipitable water. So in the region of 40 to 50, you get high precipitation events. Similarly, low OLR. So this is the on the x-axis you have or you have OLR, and you can see that the high precipitation events or the extreme events per se are basically near 200 watts per meter square. Now, if you want to do a joint PDF kind of thing, where you say where is exactly when you combine two variables, depending on the precipitation, where you get, so you can do simple plot, just do a scatter plot for these, and just do plt dot color bar. So this is so plt dot scatter will do a very easily a scatter plot for you, and you can color code the scatter plot depending on the magnitude of a variable. So what I am plotting here is SST on the x-axis, OLR on the y-axis, and yeah, I'm color coding this entire plot according to precipitation. So what happens is when you see the color bar, this is the region where you have the highest precipitation. It corresponds to low OLR and higher SST. So you can see there's a very specific area where they have a high precipitation. So basically what we are trying to do is we are trying to narrow down our domain for the model and see if the variables that we chose for defining the problem, if they are really interesting, if they are really relevant to the problem. Okay. Similarly, you can see SST and the precipitable water. So again, here is the SST on the x-axis and the precipitable water. So obviously, we already saw that for SST, this is the region on the x-axis. For precipitable water, also you will see that there is a range around which we have higher precipitation. So like 40 to 50 to 60. And similarly, we can do that for OLR. So you will see that for OLR also, you'll have a specific region for lower OLR and higher precipitable water. So we can do similar things. I would like the participants to try this with their own like other data if they have observations. And you can also see that latent heat flux. If you plot precipitation on the x-axis this time, we have a very specific value of at around 100, 120 for latent heat flux where we have higher precipitation. This one. But looking at all these plots, we can't basically say which one. I mean, we can say, okay, SST, for increasing SST, we have higher precipitation, but we can't pinpoint that. So we have to have numerical values for building the model, right? So that's what we are going to do. The first thing I have done here is I have linearized the data. So the data we had already had time, latitude, and longitude. Now, when you use scikit-learn, the regression model, it asks you. I might not have sufficient experience with it, but what I found was it was asking for two-dimensional data. So instead of two-dimensional, I just linearized the model. So this is this 1050, whatever it is, 366 into 360 into 80. So just linearize this. And similarly, I linearize the test data. Now we'll build our first regression model. So I'm starting with linear regression model, and I would like the users to basically test this with other combinations. I had tested it with all the combinations of these four variables. So to start with, you just say from scikit-learn.linear model, import linear regression. And to basically test the accuracy of the model, we'll be using mean squared error. So from scikit-learn, sklearn.matrix, import mean squared error. Now we need to predict the precipitation, right? So we have two data frames. The one is X data frame that is going to be the input to the model, and then we have training Y. So basically that is the precipitation. So after we have linearized this, I'll just define a data frame which has three columns. The first one is precipitable water. The second one is OLR, SST, latent heat flux. I'm not for this particular model right now. I'm not saying latent heat flux because when I was using all the four, the precipitable water, OLR, SST, and your latent heat flux, the root mean square error was in thousands. So I would like to figure out why was it showing 1,000. So basically, you can try all combinations. You can just say precipitable water OLR with precipitation, or OLR with SST with precipitation, or SST and precipitable water with precipitation. So here I'm showing all three because after all the trial and error that I did, I found this combination to be the best, to give the best results. And similarly, you can define the data frame for the y variable that we are going to train the model for. Okay, then you decide on the model. So since we have already said that we are going to use linear regression, you just say model is linear regression, and now we are going to fit the model. So for fitting the model with the training set, you say X data, that is the input, and Y basically the output. So this will run the multiple linear regression, and that will train the model. And so if you remember, the model will be something like theta 1 x1 plus theta 2 x2 plus theta 3 x3 and so on. So the coefficients, those are the theta that will come out of the model. Is I have printed it here. Those are something like these. So since we have three inputs to the model, we will have three coefficients. So I'm just printing the coefficients here. You can just say model dot coef underscore. So that will print the coefficients. Now to intercept, so when you have all the variables, if you intercept is basically where the line crosses the facts. So basically just say everything is given. So that is the intercept. So in our case, it is minus 27. Uh, now, after we have trained the model, let's try to uh, predict the rain on the training data itself. One second. What's it? Training data, is it? One second. All right. I might have made a mistake here. understand. So basically, you have the observational precipitation itself, and you are going to predict the rain based on the data itself, and then say what is the root mean square error between the model and the variable itself. So we'll print out the root mean square error. The root mean square error for the training data is 1.7. And now use the same model to basically do the prediction with the test data. So in our case, in the test data, we already know the output, but the model does not know it. So you just do predict test model dot predict, and you provide the input from the test. So test underscore x that we have already we have defined as the data frame with precipitable water, OLR, and SST from the test data set. And now we can compare the predict test will give the predicted rainfall, and you can compare it with the data set that we have, the basically the precipitation from TRMM from 2012. So you just say test y is from the data that we already have, and then we can just calculate the root mean square using mean underscore square underscore error, and the root mean square error for the predicted for the test data is 3.835. Okay, now we can try to see, we can plot this and try to see what comes out. If you remember, we had just linearized this. One second, so we had linearized this array. So the output will be a linear one with or one second. So the output will be in this dimension. We need to convert it back to the climatology data that we had. So 366 by 80 by 360. You can just confirm that you have done it fine properly, and then you can basically compare it. So first we'll plot what is already known to us from the test data that we downloaded. So if you look at the precipitation here, you see the structure for the test data, and similarly you can instead, so here we are saying PREC underscore mean underscore test. Here you can see you can say predicted underscore precipitation, and you so this one was already mean of 366 days, uh, and mean underscore test. I didn't show it before, but this is the time mean. So we are going to take time mean here and just compare. So if you see this one, the test, and this one, the predicted, you can see it's capturing it, and at least the features really well. This is not by accident, because I underwent a lot of trial and error for this. This is the best combination that I'm showing here. So to summarize this part, what I would like to say is, so the best combination comes from OLR, precipitable water, and SST as the input to the model. The combination of precipitable water and SST was the second best. I'll show that same example a little bit later, and now itself. And as I told you, when I included the latent heat flux, the model was kind of going up. So as a part of homework, what I would like the participants to do is run the same code as this to train the model, but instead for these combinations or any combinations you can figure out, latent heat flux and OLR, latent heat flux and precipitable water, and other. So just to show you that this one was the best and compare it with others, and for your reference so that you can do the homework easily. What I've done is I have trained the same model, but only for two inputs this time, the precipitable water and SST. So instead of here you will see train X is only for precipitable water and SST. Here it was all three, precipitable water, OLR and SST. So do that. Again, go through the same steps, and here also you will need to change because when you are trying to predict, again you will have to use only two variables, precipitable water and SST. And the root mean square error that I'm getting on the test data set for this particular one is 4.65, which is higher than 3.81 that I was getting for all the three. And even for the training data set, I am getting a little bit higher root mean square error. That is the 2.39 compared to 1.7. So let's just compare for this second model. Let's just compare the spatial structure. So this is the test one, and this is the uh, predicted one. You can see that this predicted one compared to the previous predicted one, the magnitudes are lower, and that's how you're getting higher root mean square errors. So this entire notebook, what we were trying to do is visualize what we already. So we have an assumption, okay, that the precipitation is affected by these many number of variables. To start any uh, machine learning problem per se, what you first need to do is visualize the data and try to see if it is really helpful. So what we figured out was giving the latent heat flux to the model was blowing up the model. And till the time we don't know the exact reason for it, I assume we should not use it for any further machine learning uh, algorithms. So having figured this out, let's move on to one of the examples of Kera's deep learning. Okay, so I haven't shared this particular notebook with participants. I'll do it today. Uh, so, one second. For this, so I think it's visible. You need to install Keras on your systems or whichever system you're working on. And Keras basically depends on TensorFlow. So first you need to install TensorFlow and scikit-learn, and I think SciPy also needed. But I think since it was already there on my system, it did not show me whether it was required for installation or not. So you can just say pip install TensorFlow. It will just do it for you. And then install Keras, Keras. You don't need Seaborn for now, but since I was already installing it, I just did that. So again, import all the required ones, required libraries, NumPy, Pandas, Matplotlib, X-ray, and Cartopy. And this time we are not going to open the latent heat flux variable. We are only going to use precipitation, SST, precipitable water, and OLR. And for this workshop, I was actually trying to train the model for the entire topics and for all the 366 days. But then it was going to take a very long time and I could not finish it. So what I've done is I've reduced the region. So we are going to only focus over the entire over the Indian region. So for later plotting purposes, you can just define latitude and longitude. And this time we are going to have sub-region. So sub-region is from, so if you, okay, let me just run this. So if you say latitude from 40 to 70, so the region we are choosing is 0.5 degree to 29.5. That's the zonal region for India, and we can do the same for longitude. So we are choosing from 60 to 100, and this is from 60 degrees to 99 degrees. So again, the Indian region. Okay, you can do the same thing for the test data set, and uh, for so for comparing, you can just say the mean for test data set. Also, you can take the time mean for the Indian region. Now, this is where our deep learning example starts. Uh, I'm not very familiar with deep learning, so if other instructors are there and if they feel that I might improve something somewhere or I might have made a mistake, please do let me know, and I mean, please inform the this one also, participants also. So you can just import any one of the models. So I'm importing sequential from keras.models, import sequential model, and from keras.line, so dense network, and here we have activation function. And for optimizing, we are using statistical gradient descent. So we are going to use sequential neural network for model. So if you remember, this is the same syntax used for scikit-learn linear regression. Also, you just say model equal to whichever model you are going to use. Now we have to define the model that we are going to use for the few of the parameters. Okay, so since we already know the model explains rows of data, we have three input variables. That's the SST, OLR, and the precipitable water, and layers here. So the first layer has 12 nodes, so density with 12 nodes, and input dimension is 3 already. And activation, we are using a rectified linear unit for the for a very good discussion on that. You can visit this link. I'll share this notebook with you, so you can just share this link. And I assume that for continuous variables that we are trying to predict. We are trying to predict precipitation. We have to. I mean, we can use ReLU. If I'm wrong, please let me know the instructors. So you can just run this. Okay. Now I'm again going to reshape this. We are going to define uh, an array with three inputs. So we are just saying precipitation is 439 200. So this is basically just uh, your lat into ln into time, 366 into 40 into I think 30. And similarly, you can define the inputs x. So x has three columns. One is precipitable water, the SST, and the OLR. And I was facing some problem regarding it was array of arrays. So basically, I had to stack it vertically. So this is vertical stack. And you so this will basically create so reshape. This will basically create 439,200 into 3. That's the array. Okay. Now once we have defined the model, we can define other parameters also. So for optimizing the model or optimizer, you can use statistical gradient descent with learning rate as 0.01 this time and momentum as 0.9. I think you can play around with these parameters, and I'm also doing the same basically. So you can play around with these variables and see which one fits or which one gives you the best result. So you to compile the model, once you have defined all the parameters for the model, you have to compile the model. You just say model dot compile. You define a loss function for it. So in this case, we are using mean squared error as a loss function, statistical gradient descent as the optimizer, and for the matrix for evaluating the model later, we are using mean square error again. So this is how you run the model. You just say model.fit. Xn2 is our three-dimensional array that is the input. Y is the output. Now there's something called as epoch and batch size. So and epoch is the number is an hyperparameter for gradient descent that controls the number of complete passes through the training dataset. And epoch and the batch size is basically just how many number of training samples that the model has to go through before the internal parameters of the model are changed. So if you run this, in this case, if you can see for each epoch it was taking around, so this time it is faster actually, it was for me it was taking 1 minute now. So this I just recently run, so this is taking half a minute. Okay, and when I was taking the entire topics, it was showing I think 3 to 4 hours for one epoch. So that's why I could not finish it. So I had to reduce the region. So okay, so let's say the model is done running. Uh, while running, it will show you what is the loss function and what is the matrix MSE for all this during the run. So you can see if it is reducing or it is not. And you can just say what is the final MSE error. So you can just say run this model dot evaluate, and so let's see. Okay, it's easy. Yeah. So the final MSE error that is giving is 29. I think if I can run the model for longer duration and for the entire topics, I should be getting better results here. And now we can test the model. So you define the test dataset the similar way as we define the training dataset. Let's just run it. And now for predicting, you can just say predict predictions. So predictions is basically what here predictions is model.predict classes. Okay, so you just say predictions on it. Okay, predictions. So I have to run this first. Now let's plot the test dataset first. DLT is not defined. Okay. Yeah. So this is our test dataset, and then you can do the same thing for predicted dataset. So you just say predicted underscore prec.mean. Yes, on it. So as expected, it is not trained as of now. I think it's going to take a long time. So yeah, this is all about it. I was hoping that the participants could do the same thing with as I was going along. But I hope so. This is how the entire workflow of machine learning problem looks like. I mean, you first have some hypothesis, you take the data, you do your own initial analysis, and depending on the parameters that you have, you basically choose a better model and train the model. So yeah, I hope I will get something better now. I don't know. So that's about it. Questions?
So Deepesh, there are certain questions box.
Yeah. I'll, one second. Alright. Unable to install Car2Pi module using either Anaconda, Prompt Shell Terminal, or Jupyter Notebook. So you are supposed to install Car2Pi using PIP. Uh, I don't know if you in the Prompt Shell, and Car2Pi will require you GEOS library and uh, the other library that I mentioned. Which one was that? Um, so even if you're still facing problem, just mail me the error that you're getting, and I'll try to sort it out. Uh, yeah, please zoom in. Thank you. Somebody. Yeah, so my kernel is crashing. I am facing the same problem also. So if you basically try to do something data heavy, I don't know, it should not crash, but it does crash. How do we get the test data sets? Test data sets are the 2012 data that I have already shared with on the link. Is RMSE the only way to evaluate fault accuracy? No, but I'm not familiar with others. So RMSE is basically root mean square error. You can have others also. It's definitely not the only one. Yesterday, no. Okay. So I'm not very familiar with when to use sequential and when to use functional. I think the person who is very knowledgeable with deep learning should help you out with this. Okay, please share Jupyter Notebook. Can you explain the role of momentum in SGE optimizer? I will request one minute to cover that. Theoretical parts I'm not covering because I'm actually not very familiar with those. Can you, so which question was that? Can you repeat the answer for my question? The sound was not coming. So which question is that? Okay, I think this is the one. My kernel is crashing. So yeah, I'm also facing the same problem. I think when the data is higher, or I don't know, it's very frequent. Yeah. So any other questions?
Okay, so I think we do not have any more questions. Yeah, all the GitHub links will be shared with you after this session through email, and even the notes will also be shared. So, Deepesh, are we done for the day then?
Yes, from my side, yes, rather done.
Okay. Shayanti is also available. If any of you have questions for her, you may please either unmute yourself and ask it or post it, whatever is comfortable. Still have some time, so yeah, actually, Vivek, you do your homework, and if you face certain doubts, you can either get back to us on our email ID. We are not going to really check the homework for each of you, but if you have certain doubts or if you want to discuss on it, you can email and we'll connect you to the instructor. As of now, we do not have any functionality to share homeworks and get those. Question: while working with multi-channel data, do we need to normalize the channels separately? Deepesh or Shayanti, any of you want to take that question?
Dipesh, do you want to take it? Am I audible?
Oh, yes, you are.
So yeah, so David, I think what you mean by multi-channel data is multi-dimensional data, if I'm right. Can you please? Okay. What do you mean by multi-channel data exactly? Yeah, RGB. RGB is also yes. So yes, yeah. So that is basically RGB data. Whenever you're treating, that is basically three different dimensions that comes. You can treat. I mean, we call it three different channels, but it's actually three different dimensions also. If you see, so if you're having an image of 256 cross 256, when you're having a RGB image, it will be 256 cross 256 cross 3 actually. So 3 will be the RGB dimension. So yes, you can normalize each of these dimensions separately, I would say, yes. Because if your RGB, if these values lie in very different range, it is always advisable to normalize each of the dimensions separately.